Hello there, welcome to this presentation where we'll be unpacking the chain rule. The Scottish mathematician James Gregory, who lived in the 1600s, was the first person to formulate the chain rule, and credit to him for helping the mathematics community in this way. Okay, what we're going to start with is the definition of the chain rule to see how it is formally stated and how we can correctly apply it. And of course, we'll move on to practical examples to see how that rule works. Okay, so let's get into it. The definition says the following. If f of x is differentiable and x and g of x is differentiable at f of x, then it follows that the composite function defined by h of x, which will be g composite f, this will be g f of x, is differentiable at x. And we write the following. H prime of x is equal to g prime f of x times f prime f of x. Okay, so what we have here is the fact that we have a composition of functions, and therefore we end up with an outer term and an inner term. In this case, an outer function and an inner function. All right, so this is our outer derivative, okay, and this is our inner derivative. Just take note that we keep the original inner function as it is and multiply with the derivative of g to get the full expression of the derivative of the composite function. Okay, so this takes care of the formal definition of the chain rule. We also have what is called the Leibniz notation, which is sometimes referred to as the U substitution. It's also a simplified way to write out the derivative. So for instance, if you want dy over dx, this can be dy over du times du over dx. So in other words, you write your function y in terms of u and u in terms of x, and you differentiate them individually, and the product of that will be equivalent to this. So we'll do some examples on this as well to see how the Leibniz notation works. All right, so this takes care of the introduction to the chain rule. So we are now going to move on to some examples to just interact with this rule. Let's go for it. All right, so let us do some examples, and the tip here is for you to know how to identify your inner function and your outer function so that you can proceed correctly. Okay, look at the first one. We need to differentiate h of x is equal to the square root of x squared plus 1. It's very obvious to see here that x squared plus 1 is the inner function, and we can rewrite this as x squared plus 1 to the power half using exponential laws. Okay, so our outer function is a power function, right? Our inner function is also a power function, polynomial x squared plus 1. So h prime of x, the derivative of the outer function, bring down the half, okay? Keep the inner function, x squared plus 1, half minus 1 is negative half. We multiply this by the derivative of the inner function, which is 2x. Okay, if you clean up here, cancellation happens, and this will be x over the square root of x squared plus 1. Okay, nice and easy. Let's look at number 2. Our inner function is very obvious to see that it is x squared, right? What is our outer function? It is sine, right? So what is our y prime? Y prime derivative of sine x is cos x. So this will be cos. You leave your outer function, or rather your inner function as it is. You multiply by the derivative of the inner function, which is now 2x. So y prime will be 2x cos x squared. Okay, good stuff. Here, you can see the difference here with number 2. Number 3 is square, or the power of 2 is for the function, and here the power of 2 was not for the function, it was for the input angle for the sine function. Okay, so actually you can rewrite this as cos x to the power 2. Similarity is there. Yes, so the inner function is obviously cos x, and the outer function here is the power function that is given there to the degree 2. So f prime of x will be equal to 2, right? Cos x, or 2 minus 1 is 1, okay, times the derivative of the inner function cos x, which is negative sine x. So this is negative 2 sine x cos x. Now this reminds us of the double angle identity for sine. So this becomes negative sine 2x. Okay. Good stuff. Number 4, we've got the natural number, okay, base e. And now it's the exponential function e to the root x. Okay, so if you rewrite this, e to the x to the power half. Okay, so we need to be careful here. We know the derivative of e to the x is just e to the x. But now, if you regard this as the inner function, that is our inner function, meaning this whole thing is our outer function. Okay, so dy over dx will be e to the root x times. Now I want to take your inner function and differentiate that one. It will be half x to the power negative half, a half minus 1. Okay, so this will leave us with e to the root x over 2 times root x. All right, so you just have to know how to identify your I and O, right? Your inner function and your outer function, and you are likely to proceed correctly with the chain rule. Okay, so this is what I wanted to demonstrate in this video. Of course, I encourage you to do more questions based on this rule so that you get to master this particular type of differentiating functions. Okay, so thank you very much for watching. I'll see you in the next set of videos. Keep well.